The Cassini space probe was one of the most active space probes built, collecting over 635 gigabytes of data before being lost. The success of space probe missions such as Cassini rely on a variety of factors, such as analyzing and directing the probe's path throughout the flight in order to avoid hazardous situations. In this project, we were tasked with engineering the tools for scientific discovery. So in that, we decided to create this code in order to help scientists analyze and determine the security of a probe's path within Saturn's atmosphere, much like what Cassini did.
Task 1 is being used to determine how far a spacecraft will travel and how long it will take based upon user input values. The user is prompted to enter a value of a distance he would like to reach from the core in kilometers. This data is then validated by making sure it is more than the starting distance for the spacecraft. We find the distance traveled using equation 3 from the calculations. Then the user is asked to select a fuel of either uranium or plutonium. The user will keep being asked until the fuel is chosen. The code will then calculate time taken based upon equations 4. The efficiencies were found through research and were 144,840.96 kilometers per hour for uranium and 48 kilometers per hour for plutonium. The calculations are then put out into the command window and the user is asked if they would like to do another calculation. For the test case of task 1, we input a distance that is less than the starting distance to show the warning statement and while loops work correctly. Then, when a valid distance is entered, the code runs smoothly. Next, the user is prompted to pick a fuel, and uranium is picked, which is shown in the command window. Then the calculations are done and the spacecraft travel distance and time taken is shown. For this case of a spacecraft trying to reach a distance of 100,000 kilometers from the core of Saturn while using the fuel uranium, the spacecraft will travel a distance of 69,488 kilometers over a time of 0.48 hours.
The goal of Task 2 is to determine the distance in kilometers and time in hours that the space probe must travel from its original destination to the target astronomical body. We will assume that the probe can reach the body in a straight line. The initial position is the average distance of each natural satellite from the center of Saturn. We then allow the user to pick between a ring and a natural satellite. If the user chooses ring, we'll give them a simple menu to choose from. If the user chooses natural satellite, they will be given a menu containing the first 11 of 52 natural satellites, along with the option to go to the next menu. This option allows them to see the next set of choices. Unless they choose a satellite beforehand, they will be taken to a menu that will contain the last 8 satellite choices. If they choose the 9th option to go back to the first menu, they will go through the menus again until they find the right satellite. After determining the distance of the chosen body from the center of Saturn, we will use equation 5 to find the absolute value of the distance needed to travel. We will then convert the efficiency of uranium and plutonium from miles per hour to kilometers per hour using the last equation. Then we will have the user choose a fuel type, and we will use equation 4 to find the hours it takes to travel to whichever astronomical body they chose. For our test case, the first thing that pops up onto the screen after running is the distance the space probe is from the center of Saturn, and then the menu to choose between a ring and a satellite. The user then chooses the probe to go to a satellite. To keep things simple, the user chose Prometheus, the 4th choice on the first satellite menu. The name of the satellite is then displayed on the command window along with the distance it takes to reach Prometheus from the probe's current position. The fuel menu shows up. The user chooses uranium, which has a higher fuel efficiency compared to plutonium. The fuel type and the time it takes to reach Prometheus is then displayed before our code for task 2 finally ends.
Task 3 is where we give the user the opportunity to enter their desired destination. Since there are many target destinations available, we must use menus and if statements to keep track of the chosen destination. The first menu allows the user to select the type of destination, a ring or satellite. They will then be given the option to choose between which rings and satellites. If a ring is chosen, they will also be asked to specify which epoch location to choose within that ring. We then calculate and display whether the journey to the selected target is safe for the probe. Our calculations include taking the mean of Cassini's recorded time in contact with dust for specific journeys and labeling that as the max time possible to spend on any journey where dust hazards preside. If the location selected exceeds this amount, then the journey is unsafe. We then offer the user the opportunity to repeat the process with another location. The test case for task 3 is shown on the lower left corner of the poster. We are given the menu option between ring or satellite. Selecting ring, we are then given the option between the E-ring or G-ring. After selecting the E-ring, we then select an epoch location, the 10th one from the top of the list. The results are displayed and including a warning that states the journey for the probe is unsafe. We repeat the process, but this time selecting the natural satellite method. We display the results below, the previous one stating the journey for the space probe is safe.
Task 4's main objective is to plot our time by distance traveled when the probe is moving to both the satellites and to the rings. First, we work to define our axis values by loading in our necessary data and defining variables for calculations, such as the force of gravity and the distance of the International Space Station from Earth's surface. We then use these values along with other previous defined user values to calculate safe distances for our probe. By dividing the International Space Station distance by Earth's gravity force, we have the ratio of safe distance of a probe from a planet. We then translate this value to Saturn by using its observed gravitational force. Finally, we create a subplot to display these values, with the top plot displaying the calculations based on the rings and the bottom corresponding to the satellites. The code is organized in the manner it is so that we are able to calculate all the necessary values to begin with, then use them to define all of our axes just before plotting. The y-axis, in this case, for both plots is time in the unit of hours. The x-axis then displays the distance traveled in kilometers for the ring data and then the satellite data, respectively.
We were able to create a program that would allow scientists to select ideal fuels and target locations in order to determine how far and how long a space probe needs to travel within Saturn's ring, while avoiding hazards. It's an effective model for the limited data we had. We also made assumptions that everything is in one dimension and that the space probe must be a certain distance away and can only endure dust for a limited period of time. Another limitation is that we only allow the space probe to travel the same path as Cassini in Task 3, and the time it was in contact with dust depends on the specific epoch or time that Cassini was in. Another limitation is that when we were unable to graph the 1D data that we had into 3D and label the different bodies graphed. Still, this code is the foundation for determining navigation and safety of space probe if it is modified based on 3D data and applied to other planets. Dust hazard can be avoided with real-time predictions if we progress in the future. We hope to accomplish these goals to ensure probe safety and efficiency later on.